Hello, and thanks for using TickBoom. In this video, I'm looking at the question, how many years would it take for X dollars to double if it grows at I% per year compounding? And compounding just means that every time you earn interest in a year, then the following year you'll earn interest not only on your original X dollars, but also on the interest that you've earned. So the amount that's earning interest grows and grows by more and more as each year passes by. Now, this isn't a question that a student has sent through to me. Rather, it's a question that I've often considered myself when thinking about investments and what kind of rate of return I might be earning or how long it might take my money to double. For example, if I was to put money in a bank account, how long would that take to double? Or if I was going to buy a property and expected it to double in, say, 10 years, then what kind of growth rate must that imply? Those kind of questions. So this is a good example of where you can apply your mathematical knowledge to answer real-world problems, like financial problems. If you're one of those people who's often asking, well, what's the point of learning all this math? Why do I need to know about things like logarithms? Well, this is a good example. So I'm going to work through how to apply the math to answer this question. And then what I'll also do is show a way to derive what's called the rule of 72, which is a really nice way to approximate with very simple math the precise result that I'm about to show. So to kick things off, if we say that the number of years, if we let that be n, so let's let n equal the number of years that it takes to double, then mathematically what we can say is that our X dollars compounding for n years, which means we'd say 1 plus I, our growth rate, to the power of n, that's how much the original X dollars would be worth after n years. That's what compound growth looks like. And what we want to know is how many years it takes, so what would n be for this equation to be equal to 2x? In other words, double our money. So now what we have to do is just use a bit of math to solve for n. And the first thing we can do is we can cancel out these x's, which means the result that we're going to get will be true regardless of what we're starting with, whether we're starting with $100 or $100 million, the formula that we will derive will be the same. So if I want to solve for n here, what I'll do is I'll take the logarithm of both sides. So I'll just do the natural logarithm of 1 plus I to the n equals the natural logarithm of 2. And the benefit of doing that means I can now bring the n out the front. So n log 1 plus I is equal to the log of 2. And that means n is equal to the log of 2 over the log of 1 plus I. And that is our formula. So very simple algebra, but now we have a formula that lets us pose or think about some really interesting financial questions. So for example, if I was earning an interest rate, say, of 10% per year. Now that in these days would be a very good rate of interest to earn, say on a bank account. But just for the sake of a nice round number, let's say that's what we're interested in. Then n would equal the log of 2 divided by 1 plus 10% would be 1.1. So the log. So 7.272540897 and so on years. And I've written that out in full just so that we can compare that to the result that we get when we use the approximation under the rule of 72 that I'll work through shortly. So basically, if I'm earning 10% per year, it'll take about 7 years to double my money. So that's an interesting thing to know. Using this formula, you can now think about, you could do it in reverse. You could say, well, if it took me 10 years to double my money, what interest rate would I be earning? And you could take this formula and solve for I. Now, that might not look as something that's easy to do, solving for I in this format, but actually when I get to the rule of 72, that approximation, we'll see it's very easy to work between n and I, and how to answer questions like this. You can actually pick your unknown. You could go, I know the money I'm starting with, and I know how many years it takes, so I want to know what rate of return I'm earning. Or I know the money I'm starting with and I know the rate of return I'm earning, so how many years would it take to double? And doubling is typically considered a kind of standard way of thinking about how your money's working for you. Often when people say buy property, they're thinking about how long it will take for the value of that property to double. Sometimes people want to double their money in 1 year, for example, and you know, is that a realistic thing to do? What kind of rate of return does that imply? Is that kind of within the realms of you know, a realistic goal? So this is the formula that can give you that exact answer. But what I'll do now is I'll derive what's called the rule of 72, which will let you get an approximation using much simpler math. So much simpler that you could probably do it in your head, or at least on the calculator on your phone rather than a fancy calculator. So to start with deriving the rule of 72, we need to use a technique called Taylor series expansion, or at least this is how I learnt it. There could be other ways to derive it, but the approach I'm about to show is what I learned in my first year of uni. So actually, Taylor series isn't something you would typically learn at a high school level. I learned it in my first year of uni. But you don't need to get too caught up on this. I'll show you the expansion, but it's more the result that's more important. So using Taylor series, we can actually say that log of 1 plus I can be written as the sum from n is equal to 1 to infinity of negative 1 to the n minus 1 times I to the n on n. So this result has been derived using Taylor series. If I now kind of write this out, you'll get negative 1 to the 1 minus 1 is 0, I to the 1 on 1, plus negative 1 times 2 minus 1 is 1, times I squared on 2, plus negative 1 squared I cubed on 3, plus negative 1 cubed times I to the 4 on 4, and so on. Hopefully you see the pattern. So kind of simplifying this, you get anything to the naught is just 1, so you get I minus I squared on 2 plus I cubed on 3 minus I to the 4 on 4, and so on. And where we get to our approximation is we can say this is approximately equal to I for small values of I. And when we're dealing with percentages, you know, that's quite small. So 10% is 0.1, that's a small number. And the reason we can say this approximation is when you've got a small number, something quite close to 0, then when you take that small number and square it or cube it or take it to the power of 4, it just gets smaller and smaller and smaller. And then when you're dividing by ever-growing denominators, it gets smaller again. So that all of these items, these parts of the series, become negligible in value. So actually the bulk of the value is caught up in this first term I, which is why we can say it's approximately I when I is small. So that's the first simplification, because now what we can do, and I might just turn over, we can say n is equal to the log of 2, and in the denominator here, instead of log of 1 plus I, we can just say I. And then what I have to do is, instead of writing equals, I have to say it's approximately now, because this is only approximately true. So fleshing this out a bit more, if I take the log of 2, that's 0.693147181 and so on, divided by I. If I multiply the top and bottom by 100, so I haven't changed anything, I can now write that as 69.314781 on I percent. So the denominator now is the percentage. So with, say, 10%, instead of it being 0.1, I'd actually just have 10. And now here is where you get the rule of 72. We kind of say, well, we're already dealing with an approximation here. We're not dealing with equality. 69 point something is not an easy number to deal with in your head. So why not use an easier number like 72? 72 has a lot of divisors, and it's a much more palatable number than, this long decimal. And we'll divide that by I. And so while it's not perfect, it's all right, because we weren't looking for a perfect answer in the first place. We were already dealing with an approximation. So that's where the rule of 72 comes from, and you can see that this is a much easier thing to kind of jump around back and forth between solving for n or solving for I. And you could do this math either in your head if it's a number easily divisible by 72, or just using a simple calculator like the calculator on your phone. So if we go back to our example of I is equal to 10%, you can see that 72 divided by 10, n would be approximately 7.2. 72 divided by 10 is 7.2 years. And if you compare that 7.2 with the precise answer, it's pretty close, obviously not perfect, but pretty close. So even by taking a number and just replacing it with a totally different number, we've gotten pretty close. And so you can see this approximation is a handy one to have if you want to think quickly about questions like this. How long does it take me to double my money? If I think about, say, that example with a bank account where I'm putting money in a bank account. Now, 10% is not a realistic interest rate. A much more realistic interest rate would be more like, say, 1%. That's kind of more like what you get these days. Well, okay, that's easy. N would be approximately 72 years. And so that's really quite telling, because if you think, well, if I squirrel my money away in a bank account, earning 1%, it takes me 72 years to double my money, well, maybe I might think about doing something else with it, because, I won't be around in 72 years, so what's the point? You can also think kind of in terms of assuming n and seeing what the interest rate is implied by it. So for example, if I said I wanted to double my money in 1 year, which is something that people think of when maybe they're thinking, oh, I want to get rich quickly, I want to double my money in 1 year, or every year I want to double my money. Well, how realistic is that? Because that's effectively saying n is equal to 1. So if we have n is equal to 1, we'd have 1 is equal to 72 on I percent. So you just flip these around, so you get I percent is equal to 72 divided by 1, which is just 72. So you're basically saying if you want to double your money in a single year, you're implying a 72% rate of return, which is unheard of. Like, there are not investments out there that are offering 72% a year. There's no bank account out there offering to give you 72% per year. So it kind of helps you kind of think more realistically about, how long would it take to double your money in that kind of scenario. Or if you did, if for example you bought a stock and its value did double in 1 year, literally it doubled within a year, then you've earned a stellar return, and you might want to think about locking that in, because perhaps you got lucky and you might not expect it to continue that way forever. But hopefully you found that helpful. So this is an example of how you can apply your mathematical knowledge to real practical questions, like things to do with money. I have a particular interest in these kind of questions because with my teacher hat on, I teach a financial modelling course at the MBA program at the AGSM, which is part of UNSW. So there I teach students how to apply mathematical techniques to quite broad financial questions, so usually about how to represent businesses using sophisticated Excel financial models. But I also teach a financial literacy course that I teach in high schools, where I kind of take those lessons that I teach to my MBA students and I repackage them for a high school level, and it's all framed around financial literacy. And the reason I wanted to do that is first because I thought for MBA students, for postgraduate students to first be learning about these skills, these financial skills, particularly around financial modelling, for that to be the first time they're learning this is just far too late. To have gone through all of your high school, done an undergraduate degree, worked for a little while, and then come back in, say, your late 20s or early 30s, to only be learning about these financial concepts then is just far too late. And I thought high school is really where people should be learning this stuff. And in particular, on the financial literacy front, a lot of the financial literacy education that currently happens is driven by the banks themselves. And the banks obviously have a vested interest because they want customers, and for them, customers are people who borrow money from them. So they're people who take out credit cards or loans or mortgages, and all of that involves you paying compound interest rather than earning it. And I think lessons like this help you realize, do I really want to be paying compound interest? Wouldn't I rather be earning it? There's that old saying, the person who understands compound interest earns it. The one who doesn't pays it. And so I thought, well, I don't think the banks should be the ones teaching students about financial literacy. It should be someone independent, someone who's going to teach both sides of the equation. Someone who's going to teach how to invest and how to think about money in a more holistic way, not just how to borrow it and end up kind of crushed by debt. So that's why I go into high schools and teach this stuff. If you happen to be a student at a high school who thinks your school could benefit from a program like that, you can feel free to get in touch. I'd be happy to talk to your principal or someone at your school and see whether they might be interested. You could post a comment on this video, or you could email me at nathan@tickboom.study. I'd be happy to discuss that further with you. Even if you're not at school, if you're someone who might be interested in learning more about finance and investing and how all of this stuff works, I actually have a newsletter called Money on Trees, which is aimed at helping the everyday person understand investing and kind of take away all the jargon and all the complexity and just lay it out in a simple way that anyone can understand. So just like Tick Boom, this newsletter is free. So if it is something you'd like to learn more about, this could be a good place to start learning. I'll post a comment on the video with a link to where you can sign up, because if you've always been someone who kind of wanted to learn more about finance but wasn't sure where to start, this could be a good place to start. So there you have it. Hopefully you found that helpful and interesting. I think it's a good example of how you can apply your mathematical knowledge to real practical problems. So hopefully you've been able to follow all of that. And tick boom.